So-called concavity is the next on our list of applications. With this, we're really drilling down into the details of how a function behaves by looking at its second derivative, that is, the rate of change of the rate of change. Now, geometrically, the concavity, up versus down, is determined by the position of the tangent line. Right? If the tangent line is above the graph, like it is here, then the function is concave down at that point. Right? On the other hand, if the tangent line is below the graph, like it is here, then the function is concave up at that point. Visually, I think of a graph that's concave up as having this kind of upward U shape, like it is here and here, and a graph that's concave down has kind of a downward U shape, like this graph has here in the middle piece. Now, I know there's a lot going on here, but what I'm trying to do is draw comparisons between how we determine concavity using the second derivative and how we determine increasing versus decreasing using the first derivative, since the processes are practically identical. Right? Points where the second derivative changes sign are called inflection points, and contrast that with points where the first derivative changes sign, right? Those are the relative extrema. Right? Now, a positive second derivative means the function is concave up, where a positive first derivative means the function is increasing. Right? So they kind of go up and increasing, right? They kind of match up that way. Where the second derivative is negative, the function is concave down, and again, similarly, a negative first derivative means the function is decreasing. Right, and finally, if the first derivative is equal to 0 everywhere for a function, then the function is constant, where if the second derivative is 0 everywhere, then the function must be linear. Right? And we'll talk more about that last bit in the next chapter when we look at what are called antiderivatives. So let's see how this works. Right? I have this function here, this polynomial, and I want to figure out where it's concave up versus concave down. And the way we do this, right, it's based on looking for where the second derivative changes sign. So my process here is going to be identical to the process that I use to determine increasing versus decreasing. Right, so let's see, to do concavity, I need the second derivative. Right, so let's see, the first derivative of this thing is 4x cubed minus 12x squared minus 36x. So the second derivative is 12x squared minus 24x minus 36. And now, I don't know if there's an official name for points where the second derivative is equal to 0, that the points we're going to test. Remember when we're doing increasing and decreasing, these were called the critical points, or the critical values. I usually just go ahead and call them that here as well, although I don't know if that's really I don't know that there's an official name for them. That's just the one I use since it's consistent with what we've already done. All right, so I'm going to find those points. And to do that, I'm going to set this equal to 0. And then, let's see, divide everything by 12. Let's just simplify this. This becomes x squared minus 2x minus 3 equals 0. And now this is going to factor x minus 3, x plus 1 equals 0. So I get two values to test. I get -1 and positive 3. So let's try that out. I'm going to make my number line. Right, and I'm going to put my critical values down here, -1 and 3. And I need some test points. So let's do -2, 0, and 4. Okay, so if I put negative 2 in there, and I'm really looking at this factored version here, because all I care about is the sign of this thing. If I put negative 2 in there, this is negative 5 times negative 1, which is a positive number. So the function is concave up on this interval. And if I put 0 in there, I get negative 3 times positive 1, which is a negative number, so it's concave down in this section. And finally, if I put 4 in, I get positive 1 and positive 5. That's positive, so the function is concave up here. So my answer, right, because I was asked, where is it, what's the concavity? I would say it's concave up on the intervals from negative infinity to negative 2, union 3 up to plus infinity. And I would say it is concave down in the middle from, oh, you see, I did it again. I always do that. This is a really common mistake, so I'm actually kind of glad I made it so you could see it. Be careful not to take these test values and put them in the answers, right? This should have been this value, negative 1. So then I'm going to have the middle section, negative 1 up to 3. That's where it's concave down. So the function kind of has this sort of general shape. Okay, so let you try this one, right? See if you can find the inflection points of this thing. Remember, the inflection points are the points where the sign of the second derivative changes. All right, so to do this, I need the second derivative. So let's see, f prime of x is 1 over x squared minus 1 times the derivative of x squared minus 1, that's 2x. So this is 2x over x squared minus 1. Now I'm going to take the derivative again. I'm going to get the second derivative, this time using the quotient rule. It's going to be x squared minus 1 times the derivative of 2x, that's 2, minus 2x times the derivative of the denominator, that's 2x, over x squared minus 1. All right, so let's see, now I've just got cleanup to do here. This is 2x squared minus 2 minus 4x squared over x squared minus 1. So I get minus 2x squared minus 2. Oops, sorry, I didn't square the denominator, did I? X squared minus 1 squared over x squared minus 1 squared. Okay, I need my critical values. My critical values are the points where the numerator or the denominator equals 0, because it could potentially change sign at any of those places. All right, so let's do the numerator first. Negative 2x squared minus 2 equals 0. Divide everything by minus 2. This becomes x squared plus 1 equals 0. And that has no solutions. Right? It's the sum of two squares. The sum of two squares never factors if you're limiting yourself to real numbers. And remember that's all we're working with here. So how about the denominator? Where does x squared minus 1 squared equals 0? Let's take the square root of both sides. X squared minus 1 equals 0. Now we'll move the 1 over. X squared equals 1. And then the square root of both sides. X equals plus or minus 1. So now we have to do our test, right? I'm going to do a number line. And I'm going to do minus 1 and 1. So let's pick points to test. I'm going to look at negative 2, 0, and positive 2. And okay, let's do something here. I got to see what the sign of the second derivative is at those points. But let's do something. I'm going to come back here. I'm going to factor a minus 2 out of the numerator. This becomes minus 2 times x squared plus 1 over x squared minus 1 squared. Now let's think about this for a minute. Let's think about what's going on here. I have this negative 2, and I have that x squared plus 1. X squared plus 1 is always positive. Put any number in there. Take any number you like. Take a massive negative number. When you square it, it becomes positive. When you add 1 to it, it's positive. The denominator is also always positive because whatever this turns out to be, when I square it, it is always a positive number, which means the second derivative is always negative. It is always less than 0. So you can check me on this. Go and put those points in there if you like. Right? Put negative 2, 0, and 2 in there, and you should get a negative number every time. So what's the answer? Well, the function is concave down here, and concave down here, and concave down here. So the concavity never changes. Right? It never goes from up to down or down to up. So my answer would be this function has no inflection points, and that obviously can happen. Just like it's possible for a function to have no relative maximum or minimum values. All right, so in the next section, in the next lecture, we're going to see what we can do a little more with this concavity. We're going to see how we can do what's called the second derivative test, which is another method for determining whether or not a critical point is a relative maximum or a relative minimum.